Okay. So hello, everybody. We are very happy to have with us today in our seminar, in our astrophysics seminar, Dr. Elias Roussos, who was born in Athens, Greece, but works at the Max Planck Institute for Solar System Research in Germany. He is there a senior researcher. I have personal links with this institute because it is the institute where I had worked on my PhD thesis, but that was quite some time ago, as you can imagine. And at that time, the institute was not in Göttingen, Germany, but in a small village called Lindau, not far from Göttingen. So Elias is engaged in a broad range of investigations that are relevant to magnetospheric, magnetospheric physics, planetary sciences, and generally heliophysics. He studied physics at the University of Athens and space sciences at the International Space University in Strasbourg, France. And then he moved on to Germany and worked on his doctoral thesis at the Max Planck Institute for Solar System Research. And the PhD thesis was submitted at the Technical University of Braunschweig, which was probably the university with the strongest ties to the Max Planck Institute. They had several collaborations on instrumentations on various missions at that time. I'm not sure if this collaboration continues because I know that the old guard has left. I mean,
Yes, it continues, and the new guard is also very keen in continuing. Yes.
That's good. Very good. Very useful to have ties to a technical university for space missions. So Elias, since 2005, he has co-authored or co-authored a large number of papers or book chapters on planetary radiation belts, planetary and moon plasma interactions, planetary rings, and galactic cosmic rays. And the most exciting part of his, I would say, the most exciting part of his activity is that he is a co-investigator on several experiments related to Jupiter, namely the JUICE mission of ESA and the Europa Clipper mission of NASA. And he's also the acting operations manager for the Particle Environment Package, the PEP, instrument suite of JUICE. So we are expecting, well, it will take some years before we are there, but we have great expectations from this instrument package. Elias is the recipient of 2 prestigious scientific awards by the Max Planck Society and the European Geosciences Union, excuse me, as well as an Excellence in Refereeing award by AGU. And besides his ongoing involvement in the JUICE and Europa Clipper projects, missions, he also participates on several mission or instrument development studies targeting different regions of our solar system, such as the terrestrial magnetosphere, the moon of the Earth, and the radiation belts of Jupiter, which are still, in the proposal phase, so to speak. So together, today, the talk will be on one of Elias' favorite topics, which are the radiation belts of Jupiter. And the floor is yours, Elias. Thank you very much for being with us today.
Okay, I think you have to enable sharing my screen because I cannot.
Let me check. Let me see. Multiple participants can share. So can you try?
Yeah, this works now. Yes. So, okay. Nice. Here. So can you see my screen? No?
Yes, we can see it. And now it's also full screen, so perfect.
Okay, great. So I will also use my cursor as a pointer, so hopefully you can also see that. And yeah, thank you, Yanis, for the introduction. And indeed, yeah, radiation belts is somehow became my favorite topic after I started working as a PhD student with energetic particle measurements on Cassini, which was orbiting Saturn. So at about, let's say, 2014, 2015, somehow I was very keen in just continuing and elaborating my studies on planetary radiation belts. And at the same time, that was also the period where I was, let's say, transitioning from a period where I was using, let's say, the data we're receiving from Cassini like a black box. I was just trusting them a bit too much, and I was starting questioning, how the instrument is performing, how the instrument is exactly working, all the small details. It was also the time that there was the JUICE mission, the planning of the JUICE mission was proceeding, and also Juno was approaching Jupiter. So I was slowly starting to transition and thinking how I can use my knowledge from Saturn to Jupiter. And with all this combined knowledge also about instrumentation, I started realizing that, okay, yeah, Juno will make fantastic science, JUICE will make fantastic science about radiation belts. But still, at the end, we will have a lot of unexplored regimes in this particular system of Jupiter. And is it really possible to do something about it? Is it really possible to explore this extreme radiation environment? And when I first came up with this question in my mind, I said, no, this is impossible. I mean, this is an unbelievable environment, very dangerous, and so on and so on. But in the coming years, there were some interesting developments in the instrumentation side. There was also the opportunity of the call, the Voyage 2050 from ESA, where we had the opportunity to propose new ideas for new missions. And this is when I decided to, let's say, move away from my comfort zone, which was just writing scientific papers at this time, and just try to propose something different and try to do something about this problem, which seemed impossible to solve at that time. So that's what I will do in this talk. First, I will try to convey a bit my enthusiasm about why Jupiter's radiation belts are so exciting. Then trying to explain why this is so challenging to measure the system. And at the end, I can tell you some of the ideas we have of how to achieve this and what is the status of these ideas, how far have we gone. Okay, so let me start with a slide I always use in this kind of talks, and just to make sure that everyone is in the same page with sort of a definition of what radiation belts are. So you can see a diagram here that's a diagram for the Earth's magnetosphere. It can be for any magnetosphere. They look alike, at least in these qualitative sketches. The radiation belts are situated typically very close to the planet on regions where the magnetic field is strong, and also the magnetic field lines are closed. So you need a closed configuration so that you can trap particles, and strong magnetic fields so that you can have enough stability and that you can accelerate and accumulate particles over time. And these regions, that's the regions where we really trap high fluxes of very energetic particles. So that's a large-scale component of any strongly magnetized planet and its magnetosphere. It's a region where we can see all kinds of processes which lead to acceleration. This can be for electrons, protons, or even heavy ions. And the one thing to know is that we know radiation belts of the Earth very well, but that's not just a property of the Earth. It's really a property of any strongly magnetized system. It can be a planet, it can be, if you have a strongly magnetized moon, that you can also have radiation belt. It can be a property of a strongly magnetized astrophysical object. So it's really something that fundamental in our universe that we really need to understand. And why do we care about radiation belts? There are several reasons. Of course, as I explained, these are sites where we can accelerate particles to relativistic energies. But most importantly, it's because we can actually measure these systems in situ. That's a case here. You see in this picture, that's a remote sensing of Jupiter's radiation belts. That's a radio emission from very energetic electrons, MEV electrons. But actually, we have the chance to even go there and monitor how low energy particles transition to high energy particles. And if we combine these two, remote sensing and in situ, we can do something like what I call in situ astrophysics. Second thing is that we can have the case where we can study strong interactions between particle radiation and material. For instance, one typical interaction is the cosmic ray interactions between the Earth's moon and galactic cosmic rays. But these galactic cosmic rays have very low flux, very particular spectrum. If we want to see their effects, they have to, they have to be millions or billions of years so that this evolve. While at planetary magnetospheres, planetary radiation belts, if you have a moon, let's say, surface alterations from radiation can develop and saturate over short periods, and you can actually study them very well. You can see here an example of the moon Mimas. It's a moon of Saturn, and this darker lens-type region, it's on the leading hemisphere of the moon. It's actually caused by the precipitation of MEV electrons trapped in Saturn's radiation belts. And of course, for practical reasons, we are also interested in the space weather aspects of radiation. Radiation can be dangerous for astronauts, for instruments, so we need to know where we are sending people or where we are sending spacecraft and instruments to measure and perform according to our desires and specifications. Okay, so the next point I want to make is like, how do we study radiation belts? And maybe the first thing that comes to mind is why don't we just study them at the Earth? At the Earth, the radiation belts is the first thing you encounter after you launch with a rocket. It's the first discovery of the space age. So you launch, after a few hours, you release your spacecraft, and you are embedded within the radiation belts where we have components like electrons, protons, and also we have a weak component of heavy ion radiation belts at the Earth. So why don't we just send more spacecraft and more advanced instruments? We have, the opportunity to send heavy instruments, get a lot of data down. So why don't we just do very detailed studies at the Earth? And another way to put it is really, are the terrestrial radiation belts a prototype for all others? So can we get away just with more detailed measurements? And in some cases, we can actually do that. So I have shown here, this is a plot. This is distance here, or what we call the L cell. And that's the flux of high energy protons in Earth's radiation belts. And these protons are actually caused by cosmic ray interactions. So we have cosmic rays hitting the atmosphere of the Earth, producing neutrons. And then some of these neutrons will beta decay within the strong magnetic field regions of the Earth, and they will get trapped and form this high energy component that you see here. And the same exact process happens also at Saturn. In which the case of Saturn, we can also have cosmic ray impacts at the rings, not just on the atmosphere, but the principle is actually the same. So these proton radiation belts of Saturn are produced through the same process as at the Earth. But for the same planet, there was a very prophetic, I would say, article in the 80s. You can see the title here. If you have seen one magnetosphere, you have not seen them all. And actually how energetic particle observations in the Saturn magnetosphere helped us resolve that. And after several decades of observations at Jupiter, Saturn, Uranus, or Neptune, what we have understood is that there are a lot of factors that can change, that can modify a radiation belt system. You might imagine that the magnetic field strength plays a role, but even parameters like the magnetic field orientation can play a role. Like for Saturn or Jupiter, for instance, if the magnetic field was oriented south to north instead of north to south, as it is now, then the proton radiation belts would have been much more stronger and the electron radiation belts would have been much weaker. Planetary rotation rate, the presence of moons or rings within the radiation belts, they play a role. The properties of the planetary atmosphere, of course, the solar wind, the external forcing also play a role. And you can see also an example here. So This is measurements, where this is energy here on the horizontal axis, that's time. And this we have the color shows fluxes of electrons and fluxes of protons measured from Cassini. And you see these bursts of radiation here up to hundreds of kilo-electron volt for electrons and ions. And these bursts of radiation are caused because of a process which is called centrifugal interchange instability. And this process is really driven by the fast rotation of the planet and the presence of moons at Saturn, and Enceladus in particular, which is mass loading the magnetosphere with material. So this process can actually not occur within the Earth's magnetosphere, and we need to visit other planets to start getting, let's say, different ideas of how radiation dynamics actually work. So in principle, what I want to say is that acceleration processes and particle and radiation material interactions, they are very limited in the terrestrial magnetosphere. And that is why we also need to study these systems away from our own geospace. And let's say if we only had the choice to select one of the radiation belts to visit, of course, my choice at least would have been Jupiter. And I want to argue why this is the case. So first of all, Jupiter, as you know, it's the largest planetary magnetosphere we have in our solar system. So you see here, that's a sketch of the magnetosphere, but actually to scale, this is the size of the Earth's magnetosphere. You can practically fit it within Jupiter, or even, let's say, a few Jupiters across. The magnetic field that is generated within Jupiter has a magnetic moment which is about 20,000 times stronger than that of the Earth. Combined with an internal source and also the weaker solar wind, you get this enormous magnetosphere here, and a very strong magnetic field region close to the planet, far away from the solar wind, which is relatively undisturbed all the time. And within this magnetosphere, close to the planet, what we can see is really an extreme radiation environment. You can see here some images. These are generated by simulations using the Salambo code in Onera. So that's the electron component here with fluxes above 21 MeV, and here is a proton component with fluxes above 80 MeV. And just focus here for a start at the electron component. And we compared some synthetic spectra, some spectra that we think they look like this currently at Jupiter in red, and compared to the Earth at L equals 8.3. And just notice here that 8.3 is somewhere here in the radiation belts of Jupiter, whereas we compare with a spectrum much closer to Earth and much deeper in the outer radiation belt of the Earth. And while you can see that at low energies, or relatively low energies below 1 MeV, the fluxes are similar. When we go above 1 MeV, especially towards ultra relativistic energies above 10 MeV, the difference in flux is enormous. And that's already something to think about, like where do you get all the source material, the source electrons, and how do you accelerate them so much when you start even with the same boundary conditions compared to the Earth? And imagine that this difference is even bigger if you go really in the core of the radiation belt. And the same comparison applies if you think about protons, if you think about heavy ions, where you have also sulfur, oxygen, and even other trace species in the Jovian radiation belts. And the other point is here that I was talking about what happens very close to the planet, but in reality, the radiation belts of Jupiter, they don't really have an outer boundary. These are measurements by the Galileo spacecraft, by Coleman, so he did a long-term averaging of all the measurements by Galileo. And this green line here shows electrons with energies of something like 30 MeV. And you see that the extent they really feel you can measure a signal all the way to large distances. 100 radii here is more closer to the magnetotail region, but all the way to the magnetopause, you can really measure relativistic electrons. And of course, a lot of these electrons, if the magnetosphere opens there, if you have a reconnection event or any other process, some instability, they can escape. And then you start filling the whole heliosphere with relativistic Jovian electrons, and that's time profile of relativistic electrons from the Pioneer 10 spacecraft across several years. So it was launched from the Earth. Here you see some solar events, but the background flux, you see it's increasing towards Jupiter encounter and decreasing afterwards. And these are all relativistic electrons filling all the distances between Saturn and the Sun with energetic electrons up to energies of about 10 to 20 MeV. Above 10 to 20 MeV, then the galactic cosmic ray electrons, as you see here, they overtake the Jovian ones. So it's really a powerful accelerator. And it's also interesting that within this system, very deep and continuously embedded within the radiation belts, we have a series of moons. The most known moons are the Galilean ones. Here you see Io, which is also volcanic and causes the formation of this torus, which we call the Io torus. We have Europa, Ganymede, and also Callisto at the edge, at the outer edge of the intense radiation belts of Jupiter. But it's not only that. Let's say the less popular moons are still present, like asteroid-sized moons, much closer to Jupiter and much more deep in the synchrotron radiation region of the electron radiation belts of Jupiter, plus a ring system. So this ring system is actually formed from material released from these moons here. They are called Amathea, Phoebe, and also Adrastea and Metis, which they share the same orbit you can see here. And of course, you know, there is some back and forth interaction between the moons and the magnetosphere. And if you like also the topic of space weathering from a planetary science perspective, you can imagine that these are the most weathered and most radiation modified moons that we have in the solar system, continuously exposed to radiation levels that are like 8 orders of magnitude higher than the fluxes of cosmic rays, for instance. Okay, and the presence of all these moons also, and rings and active moons, causes this magnetosphere to have a very particular ion composition. So here you see composition measurements. This is in the MeV range, this is in the KV range, but the dominant species. And we see a lot of other trace species. Some come. We are not. The point to make here is that first of all, the fluxes of these ions are very high, and also these ions, they do not have a single ionization state. So you can have oxygen singly charged, doubly charged, multiply charged in general. So if you want to study processes which are dependent on the mass of an ion, but also on its charge state, Jupiter is the place to go without a problem. By the way, I see some signals here that my connection is unstable, so if you cannot listen me well, please let me know.
Ηλία, να σου πω, μ' ακούς έτσι?
Ακούω, ναι.
Θα έλεγα να σταματήσεις το βίντεο το δικό σου για να βοηθήσεις λίγο το upload, να μην έχεις δηλαδή... Ωραία. Για να σε ακούμε, είχε κάτι μικροδιακοπές προηγουμένως. Νομίζω ότι έτσι θα είμαστε καλύτερα.
Okay, μια χαρά. Okay, I continue, switching also language again. And where was I here? Okay, so I would say that another unique quality of the Jovian system is that it really glows. It's the only magnetosphere we know in our solar system that really glows in so many different wavelengths. You see here, it's an image of the electron radiation belts of Jupiter in radio wavelengths. That's actually the first magnetosphere we discovered, is the Jovian one when we used our radio telescopes, besides the one of the Earth, of course. We knew the Earth was magnetized, but we didn't know the form of the magnetosphere. We knew another planet was magnetized when we saw the radio emission coming out from Jupiter in the 1950s, end of 1950s. Recently, we were able even to image the electron radiation belts of Jupiter in X-rays. X-rays have also been used to image heavy ion interactions with the Io torus. We have seen here, you see the weak color emissions at the low latitude atmosphere of Jupiter, again in X-rays, which is a revealing process of precipitation of heavy ions. We can also see the Io torus We can image it in UV wavelengths. Here this is not caused by high energy radiation, but from plasma. But still, through this kind of emission that we see here, we have some indirect evidence of the type of plasma flows that we have in the magnetosphere, which are also linked a bit to the dynamics of the radiation belts. And why this is important? Because remember that recently, at the beginning of this year, first of all, we had the first two papers published, one in Science, one in Nature, about the same object, where we have seen the same thing as we see at Jupiter, synchrotron radiation belts around brown dwarfs, this time resolved, not just as a point source. So maybe that's, let's say, this 2024 is a year that for at least the radiation belt community, we discovered our own version of exoplanets. So we can actually have more samples of radiation belts, not just the ones of our solar system. And then we have a much more statistical sample to compare with our in situ measurements. But the important thing is that this is a system that we can sample in situ and observe remotely. And for understanding these systems here, that will be very, very important. It's also, I have something here which is a bit funny, but it's also something to remind you how unpredictable and complex the Jovian system is. So there was always a suspicion that we can treat Jupiter as an astrophysical radiation belt. And there were some papers written in the 70s and 80s about this topic. And in speculating what might be going on at Jupiter, here you can see one sentence I highlighted, yet we do not suppose that Jupiter is able to beam MEV electrons and ions up into its magnetosphere. And surprise, surprise, Juno arrived at Jupiter. This is a time series of MEV electron measurements above 10 MeV by the radiation monitor of Juno. And here you see, away from the radiation belts, mapping to the polar magnetosphere, you see actually greater than 10 MeV electron beams coming out of Jupiter impulsively through a process that we still cannot understand. So imagine that this knowledge can actually go and, let's say, inform us about things that we consider as being impossible at another, let's say, exotic astrophysical radiation belt or magnetosphere. Okay, so that's all I want to say about the Jovian magnetosphere as an introduction, as a top-level introduction. And now you might question yourself, like, what is the origin of Jupiter's extreme radiation environment? And that's a question that you see written in many papers, in many proposals, even in many popular science articles like this one here. And the typical, let's say, also top-level response to this is that it's because Jupiter has this combination of strong magnetic field, a very strong plasma source within its magnetosphere from Io, from volcanic Io, and also the magnetic coupling of all this with the fast rotation of the planet. It's not just Frank Bagenal who says this, many people say this, I have even said this in my papers. But you know, in reality, the answer is not that simple. And to just say some counter arguments against this statement here, just think about the system we know best, the radiation belt system we know best. That's the Earth's radiation belts, the outer component and the inner component separated by the slot region. And the strongest component that we know now from the Van Allen probes mission, and we also know it for some time before that, is the outer radiation belt, which is sitting in a region of a weak magnetic field. You go to stronger magnetic fields, you have the slot region where you have no radiation belts. And the inner radiation belt is present there at even stronger magnetic field, but it's much, much weaker, as we know now from the outer radiation belt. So you see here this statement, strong magnetic field, maybe it's a prerequisite to generate strong radiation belts, but it's not a necessary condition. And we can have the same arguments here for the other parameters or factors that may control Jupiter's radiation belt. The point is that this is a good suspicion of what might be causing Jupiter's radiation belt to be so strong. But the way that these things are coupling together and generate the system is really not known. And maybe there is no, the reason is completely different. But what this suspicion might tell us is that, let's say, we cannot study the Jovian radiation belts in isolation. So it's not enough to go there, get some energetic particle measurements in the most intense region, then we are done. We have all the data we need and we will solve the problem. If this suspicion is correct, then we need to study this in the context of the whole magnetospheric dynamics. We need to understand also how plasma is working. We need to understand how Io and the moons contribute to the balance of radiation, the sources, the losses in the system. So it's really a multi-component and multi-dimensional system that we have to study. Okay, so what are the minimal, let's say, observational considerations when we want to study Jupiter's radiation belts? First of all, is as much as possible sample the magnetosphere globally. When we study a magnetospheric system, it's like we study a weather system. And we should also care about timescales. Timescales for Jupiter, timescales of variability are days to years, I would say. And of course, we need this to put the observations in context to Jovian system dynamics, and we should also we cannot ignore the moons within the magnetosphere. Of course, we should not forget that this system here is enormous. So compared to the Earth here, you see the scale of the Earth here, and it's very difficult to have a global mapping and also trying to study the variability of this system, capture all the time scales, with a single spacecraft. So in principle, remote sensing imaging of the magnetosphere or even Earth-based remote sensing is really important if we really want to capture the dynamics of the system. So on top of in situ measurements, we really need also whatever we can get, like aurora imaging, Io torus imaging, the radio emissions from the belts, and so on and so on. And of course, we have to really extend to energy regimes that we do not have in our terrestrial radiation belt system, and we do not even have at Saturn. So we have to go really to energies greater than 50 MeV for electrons and maybe much, much higher than 100 MeV per nucleon for ions or protons. Plus, achieve in these energy ranges high energy, angular, and mass resolution. And of course, we need context measurements. So what we have learned from the Van Allen probe's mission at the Earth is that you cannot just measure energetic particles. You also need the context for magnetic field, waves, and also thermal plasma. So what we are doing now to explore Jupiter's radiation belts, or what we have done in the past, we started with a series of flyby missions in parallel with observations of the radio emissions from Jupiter. Then Galileo was the first orbiter. Currently, we have Juno ongoing in orbit. It will keep going until at least 2025 in orbit around Jupiter. And in the near future, we will have JUICE arriving in 2031, and about 1 year earlier, we will have Europa Clipper also arriving in the system. And all this is complemented by a series of Earth-based observations, like a series of space telescopes here. This is in EUV, this is in X-rays, also Chandra in X-rays, and also this is in the UV wavelengths. But let's see, with all these resources, how well we are doing. If you see here, these are some characteristic orbits from flyby missions, also in blue here, the Galileo spacecraft. You can see also the Juno 1 perijove, and you can see that most of the coverage is restricted up to somewhere here, 9 Jovian radii, that's the orbit of Europa. And the coverage here is much more limited. And there is a very good reason for this. I mean, the spacecraft engineers or even the scientists are quite scared to go in here because the radiation dose which is experienced by the spacecraft here is really enormous. So what you can see here in this plot is as a function of distance, the amount of rads per day, the total ionizing dose of rads per day that you can get as a function of distance from Europa for different amounts of shielding. So JUICE has about a shielding of about 5 to 8 grams per square centimeter on average. Let's take this value here, and you can see that in the core of the radiation belt, somewhere here, you get within 1 day about 100 kilorad. That's the radiation design limit without any margins for JUICE. So you have JUICE. So after all this protection you put on JUICE, you put it here in 1 day, probably you lose the mission. You stay at Europa, maybe you can survive about 1 week, and you achieve this radiation dose levels. So it's a really dangerous environment to monitor. And also it's very difficult, radiation is very difficult to shield. So it's not, let's say, even if you have the resources, if you have a lot of mass that you can add on your spacecraft and put a lot of shielding, after some time, after some amount of shielding, let's say here about 20 millimeters equivalent aluminum thickness, your radiation dose doesn't drop anymore because that's from electrons. You stop electrons, the electrons generate Bremsstrahlung, and this will propagate in your electronics. So it's really difficult to avoid radiation even with a lot of shielding. And the way to regulate this problem is actually to regulate the exposure time of your spacecraft into the regions of extreme radiation. So you need both shielding and also regulating the exposure. And if we want to really visit the core region of Jupiter's radiation belts, then the type of Juno orbits that you can see here, highly elliptical orbits crossing very fast through the inner radiation belts, is the way to go. Of course, we then need instruments that can measure very fast. And because these orbits take very long to complete, we also need some kind of an imaging method to complement our measurements and also get a global perspective. So let's say we have this kind of orbits, then we need to choose an imaging method. So what do we choose? There are many different ways to image a magnetosphere. And currently, some of those have been applied, like for instance, UV measurements. We have them from the Earth. We have them from Juno. We have them also on Galileo. And you can see here, we will have them also on JUICE and Europa Clipper. That's a UVS instrument, gets these nice images here of the aurora. It can also image the Io Taurus. So that's something very useful, but still it monitors the, let's say, the soft energetic particles at KV range. And also that's something that we can do from the Earth, and we have been doing with many spacecrafts already. The other thing that we can do is imaging of energetic neutral atoms. So this is a way to monitor the energetic ion population, the singly energetic ion population when you have a lot of neutral gas. We have a lot of neutral gas because of the Europa and the Io Taurus. And then you can charge exchange. And then when you charge exchange, these ions become neutral atoms with a high velocity, so they will propagate like photons, and you can actually take pictures of them. And we will have actually the first energetic neutral atom imagers on JUICE, one for high energies, this is called JENI, one for low energies, this is called JNA. The problem here is that you can only probe singly charged ions, and also for energies below about 300 keV, because the cross-section for charge exchange drops substantially above those energies. So that's a disadvantage, let's say, but anyway, we will get fantastic measurements from JUICE on this. The other way of doing imaging of the radiation belts is to continue doing some radio imaging of the electron belts close to the planet. Again, that's something that we can do from the Earth. We can also do it from a spacecraft, but actually not much better compared to what we can do from the Earth. Plus, the instrument is really a really heavy component to put on a spacecraft if you want to get this kind of images here. And yeah, the other problem is that with this kind of observations, you can only monitor MeV electrons and also monitor in the regions where the magnetic field is strong. So the synchrotron emission is not dependent only on the flux and the energy of the electrons, but also on the strength of the magnetic field. So even though the radiation belts of Jupiter are slightly stronger a bit further out, you cannot see the emission from there because of the weaker magnetic field. So what can we do? What can we choose? Is there a better solution? And actually, there is one, X-rays. Here is a table. I don't expect you to read all the details here. Maybe the main message from this table here is that you can monitor with X-rays all kinds of regions, and different regions, different types of particles, and also different energies. So it's really a very powerful imaging technique that we have done it from the Earth. You can see some images here of the radiation. This is the electron radiation belts. These are which are caused by inverse component scattering photons from the electron populations at Jupiter. And we have taken images of other components of the system, equally interesting. But you hear that's actually an image of Europa with precipitating ions on Europa. And the spectrum that got the X-ray spectrum from that is just not more than 15 counts if you sum them up here in total. If you put, and this was done with the Chandra Space Telescope, which weighs is an inch of one, really 1 ton telescope. If you actually take a 10-kilogram X-ray telescope, like what we are going to put on the SMILE mission, which is going to launch very soon in orbit around the Earth. If you take the SXI instrument on SMILE, it's the one here, about 10 kilograms, then within half a second, you will generate all the counts, let's say in proximity from Jupiter, that you have collected over 40 years from X-ray telescopes from Jupiter, from the Earth. You can see here, for instance, how you can, this is aurora X-ray emissions during active times and during quiet times, and as a function of distance from Jupiter. That's the level of counts we get from the Earth. That's the level of counts we get from Jupiter. And the fact that we can really monitor different species and populations and also regions, that's also really fantastic. So I think, and the team which is behind this agrees that really X-rays is the way to go. The other bigger challenge and problem we have to solve is about charged particle instrumentation and the issue of the penetrating radiation. So typically the missions that until now we are sending to Jupiter, maybe with the exception of Juno, are really multidisciplinary missions. They carry cameras, spectrometers, mass spectrometers, also energetic particle detectors. But of course, the mass allocation for each experiment is really limited, and typically for particle detectors is the most limited among all. Here is, let's say, one typical energetic particle detector we had on the Galileo probe. That's a probe that went into the atmosphere of Jupiter. And before that, it crossed the radiation belts and it measured the distribution of particles there. And that's a typical design. You have a stack. Here it's a diagram. You don't have to understand the details, but it's usually some solid state detectors in a stack here. And by coincident measurements, energy depositions on these detectors, you can actually get some idea of the energy, the direction, and also the type of the particle you are measuring. Problem here is that if you are dealing with the energies that you have trapped in Jupiter's radiation belts and the fluxes, first of all, you cannot stop them with the shielding that you have all around this detector. So you actually, particles penetrate, they reach the detector in a non-nominal way. And of course, that's a problem because this destroys any kind of energy resolution you might have. And you end up with what you call integral channels. So that's one response function of an integral channel that you have from this kind of detectors, where you measure everything above a given energy. So you have no energy resolution, and the same channel, even though it was designed to measure electrons, of course, it has the same response for protons. So that's actually a problem. And currently, that's the biggest problem we have at Jupiter. We have a population, especially above 1 MeV, for which we do not have energy resolved measurements. And if you don't have energy resolved measurements, you cannot do spectroscopy, and that's of course a big minus in your investigations. And that's a problem that will not be fully solved with JUICE and Europa Clipper. With JUICE, we are going to do a bit better, but not go much above, let's say, 10 MeV with some energy resolution. The spectrum at Jupiter can even go for electrons up to 100 MeV. For ions, it can go up to several giga-electron volts. So we really need to cover this energy range. I can show you what problem penetrating radiation causes. Here is a case from the MAG-ICE instrument on the Van Allen probes in the Earth's radiation belts. And you can see here two spectrograms. That's as a function of L-cell or distance. This is time on the horizontal axis, and the color shows the electron flux at 1.5 MeV. And if you get the data unprocessed, you see here the component of the outer radiation belt as a function of time. And that's the part of the inner radiation belt that for many decades, we were thinking it was quite intense. And you can actually see it here on the MAG-ICE instrument. It's quite prominent in the unprocessed data. Luckily, this instrument is very capable and very quite advanced. So of course, when all the cleaning method and data analysis method and processing was applied, that was what we realized, is that we really have no inner radiation belt above 1 MeV at the Earth. So what we were thinking all this time, that this is really electrons, was actually protons penetrating the detectors and leaving a false signal here. And that's the black here is the typical spectrum that we have now after the Van Allen probes. And you can compare it maybe with this blue line, which is the 50% spectrum that we have at the Earth before the Van Allen probes. And you can see at about 2 MeV energies, there is like a different influx of about 1,000. And that was a problem at the Earth's radiation belts. You can imagine how big this problem is at Jupiter's radiation belts. So how did my guys try to manage to solve this problem? The technique that was used is magnetic spectrometry. So you are actually guiding electrons with a magnetic field to different detectors, and you know that the curvature radius here applies to only specific energy. So the energy deposition you should also have here should correspond also to this curvature that electrons of the specific energy should have. So this is what we call a coincidence measurement. And this kind of coincidence would be very, very important also to apply for Jupiter. But of course, because at Jupiter we got much higher energies, the problem is that we need to use stronger magnets. And the stronger magnets, of course, they can interfere with external environment, especially if you have plasma measurements. They can disturb the plasma that arrives at your detector. And we want to avoid this. They can disturb the magnetometer measurement and so on and so on. So it's not an easy solution. Plus, all these techniques, even on my guys, they rely on the assumption that you can actually stop the particle on the detector. If your particle has enough energy, even if you manage to deflect it, but it has enough energy to penetrate your detectors, then this technique is not really useful anymore. So we need also to think about a different approach. Maybe I will skip this slide in the interest of time. I can say that Van Allen probes had another instrument which was not so much used, but maybe that gives us some guideline for what we should do on Jupiter. And this was called the RPS instrument, a relativistic proton spectrometer. And the way that it was measuring particles, it was through the Cherenkov radiation that they emit. So if you actually have particles which move in a medium at a velocity higher than the velocity of the speed of light within this medium, so they emit Cherenkov radiation, and the photons emitted are proportional. The amount of photons are proportional to the energy of these primary particles. This detector was optimized for proton measurements at the Earth, but by accident they found out that this can actually measure greater than 30 MeV electrons, and with some good energy resolution up to about 60 to 70 MeV. So that's maybe a solution that we have for Jupiter. The other possibility comes from CERN, and these are some detectors which are called time-pix detectors. It's essentially like a CCD camera here, with a different. So it's a highly pixelated solid-state detector with a difference that this kind of CCD camera here, it can also give you information on the energy deposition of the particle. And not only this, the spread, if you have a particle hit, the type of spread that you have from the different particle, it can even give you information like here, you see this thick particle here, that's a proton, because usually proton or a heavy ion will deposit a lot of energy and very focused deposition. These stripes here might be from electrons. Other ones, they can give you information about gamma rays and so on. So it's really a powerful type of detector. It gives you a high precision hit position, plus energy loss information. So if you take certain layers of this detector and put a magnet, it doesn't have to be very, very strong magnet, but it's enough because of the high hit position that you have. It's enough to deflect your particle just a bit. And then through the different layers here, this detector concept here, which is called PIXSpan, it has 6 layers of these detectors, time-pix detectors here. So if you measure with precision the position of the hits, you can actually reconstruct the trajectory of the particle, the electron or the ion within the magnetic field, and get energy resolution up to GeV energies with high precision. This type of instruments, until recently, they were coming in the range of 100 kilos or above, but this instrument concept is now where we have actually built a prototype for it. is down to a mass of about 10 kilos, which is making it a bit more realistic for Jupiter. Okay, so these are all ideas that we have. Let's talk about what is the latest developments and the status of all these ideas. This all started, as I said in my introduction, with a white paper in ESA's Voyage 2050 called The In Situ Exploration of Jupiter's Radiation Belts. And I think this was well received also in the other side of the Atlantic. And 3 years after, we got actually funding from NASA to pursue with this idea. You can see here, this mission is called now COMPASS. It's the same cover actually here, but now we have a spacecraft here on the cover, as you can see, which is good news. We're evolving. So this COMPASS mission is actually a funded mission concept study, which is under development and is currently considered for NASA's heliophysics decadal survey. So we will know the results of this decadal survey. We are very hopeful to get a very positive feedback so that we can continue with this idea or even go ahead with this idea immediately. That's the ideal outcome of this survey. We will hear about this late in the summer or maybe in September. So we're really hopeful. Of course, this is driven by the heliophysics division of NASA. So all the goals, the pillars of the science we want to do with the COMPASS mission are, let's say, more heliophysics focused than planetary science focused. But of course, if you go to Jupiter, you cannot ignore the planetary physics component of what you are doing there. Another point to highlight here, usually we don't look at this, like who is involved in this project, but maybe it's quite remarkable to notice that even though this is a NASA-led proposal, half of the institutes which are involved here are European. And one reason is that also this idea also started from Europe. So what is this mission looks like? Here you see, as we said, we have the Juno type of orbits, but we're a bit more daring. So we start with high inclination, long eccentricity, high eccentricity orbits, and gradually we become more daring and we start going not closer than Io. We have a series of Io flybys, and then we also use Ganymede and Callisto to put the spacecraft closer and closer and closer, and then towards the end, reach and sample the equatorial, most intense radiation belts of Jupiter. We have a series of instruments considered, a lot of particle detectors, but also the context measurements we need from magnetic field and plasma waves, plus, of course, the first X-ray imager we consider to fly for proximity X-ray observations in Jupiter. Okay, so that's all I wanted to say. As my final slide, I want the takeaway message to be that really Jupiter's radiation belts are one of a kind in our solar system. You might have, all of you might have different interests here. Some might like radiation belts, some might find it boring. But if you like astrophysics, also Jupiter, that's a place for you. If you like planetary physics, you can do a lot of planetary science between material interactions between the radiations and the moons or the rings of Jupiter. But at the state of the art, currently where we stand is we know that we still need to make developments when it comes to mission design. For certain types of instruments, we also need new ideas, new instruments, new capabilities. But at least the positive message is that Galileo, Juno, and what we expect we will see from JUICE and Europa Clipper is that this task of studying the radiation belts of Jupiter is a feasible one. So JUICE and Europa Clipper will advance really the state of the art, definitely, that's no doubt about this. But many aspects of the Jovian radiation belt system will remain still out of reach, in particular the core region of the radiation belts close to the planet. But we have a positive development. We have a mission concept study. It's currently under consideration from NASA's heliophysics division. And hopefully we hear good news and good recommendation about it really soon. And if you want to know more details about COMPASS, you can always reach out to me, or the PI of this mission is George Clark. Some of you know him well. And yeah, you can also reach out to him. I'm sure he would be happy to provide you any information. And with this, yeah, I conclude my talk, and I'm happy to get any questions that you might have.
Thank you very much for this very interesting and inspiring talk, Ilya. So we are open for questions. Please feel free.
So I will still keep my slides on, so I do not see your faces. So please let me know your name when you ask, so I can respond. Thank you.
Δεν βλέπω κάποια κινητικότητα. I think let me ask something which is not absolutely directly related to your presentation. You probably remember the suggestion of Nishida that Jovian electrons might be a source of the terrestrial radiation belt electrons. Are you aware of any evolution of that suggestion? I know it's very difficult to test this hypothesis for many reasons, but I was just wondering because the Jovian environment is indeed very rich in this kind of particles, and probably that was the main reason for Nishida to suggest this.
I know about this idea. I'm not sure from at least my quick literature survey about this topic. I didn't get the impression that this idea was followed up. So I'm not sure if there is any conclusion about it. And my feeling would be that there might be a weak component at best in the Earth's radiation belts that might be sourced by electrons, but to the level that I was able to follow the Van Allen probes mission and all these amazing results, I see that the variability of the electron radiation belts, and especially at the MEV range, where, let's say, the Jovian electrons would have the highest contributions, I see stronger and more obvious responses to, let's say, solar wind transients and also wave activity within the Earth's radiation belts, which might mean that at least the regulation of the dynamics is really controlled by other processes. Maybe part of the initial source might come to some extent from Jovian electrons, but my expectation is that this would be a very, let's say, weak contribution. If it's measurable or not, I'm not sure. The way to test it really is to try to find the 13-year periodicity that we have. That's the 13 years is sorry, not 13 months, not 13 years. 13 months is the synodic period between Earth and Jupiter. So every 13 months, we transition from a very good magnetic connection between the Parker spiral between Jupiter and the Earth to a bad connection. So kind of like a solar cycle. It's very close to the solar cycle, 11 years, which might complicate things. But if one can resolve a 13-year component in the electron fluxes and variability at the Earth, that might be the, let's say, the proof.
Yes, of course, magnetic connectivity would be essential for such an influence, because that would be the only way to have electrons coming to geospace from Jupiter. Any question from the audience? Είμαστε και όλοι Έλληνες.
Okay. Μπορούμε να το γυρίσουμε και στα ελληνικά, δεν υπάρχει θέμα.
Well, it seems that your presentation was very detailed and fully understandable, I guess.
That's good.
So what is the timeline for COMPASS? I mean, when do you expect to have some news on COMPASS?
So the recommendation from NASA's from the decadal survey from NASA's heliophysics division would come, I think, late summer or early, let's say September, sometime in September, the latest. Based on that recommendation, of course, it might be deemed that you are good to go, so please proceed ahead. This is the first mission we select. That would be the ideal thing. There might be the possibility that this is a nice concept, but you need some more technological maturity, and please develop this study further. The worst case scenario is that this is termed, of course, infeasible or immature, and you need to start over or something. We do not believe we're at this stage, but let's say in the best case, if the mission is selected immediately, the earliest that such a mission could launch is not, I would say, the beginnings of 2030, probably not much earlier than 2035, I would say.
Okay. I'm happy to see the Geneva instrument involved in this. The one that you showed, actually, you probably, well, I want to show you a picture here.
Okay. Should I stop sharing, maybe? Yeah.
So you are probably aware of this.
Yes, that's actually, when I was saying in my introduction that at the time that I started thinking about Jupiter, and I declared, no, it's impossible to do it, this instrument that you see here, PAN, was proposed, and I was not the reviewer of this proposal, but somebody reached out to me and asked what I think about this. The reviewer reached out to me and asked me what I think about it, and I said, okay, if this works, maybe we have hope. So that's how I learned about the Geneva instruments.
I was not the reviewer of the proposal, but I was the reviewer of the project. So,
okay.
And it was very impressive. I mean, the instrument, the capabilities of the design of the concept are very impressive. They have, for the time being, they have a small prototype. It's a mini pan still.
Yeah, so I actually went to University of Geneva. I was asked to give a seminar there, and they showed me Minipan. It's not the typical energetic particle detector. It's much, much heavier than we are used to it. But it's still, if you have a dedicated mission, instead of, let's say, reserving this mass for a camera, you can, let's say, reserve it for an energetic particle detector. And yeah, the new version of this Minipan, which was actually deemed a bit too complex for the COMPASS mission, is PixPan, which only uses the pixel detectors and coincidence between pixel detectors. So it doesn't use scintillation, it doesn't use photomultipliers or any component like this. The Minipan is a nice concept for cosmic rays, but maybe too slow to measure the high fluxes of Jupiter's radiation. But PixPan is, let's say, the variant of Minipan.
Okay, so let's see. We have some, thanks by Savas, Kostas, and Anesina. Many thanks for the talk. And I think that we can again thank you for the great presentation, and wish you all the best with your scientific endeavors.
Thank you very much. Thank you for giving me the opportunity to talk.
Thank you, Ilya. Thank you very much. Take care.
Καλό απόγευμα.
Γεια χαρά.